Right, so we have the Mark length spectrum, and now the conjecture is that this extra information should be enough to determine the metric up to isometry. So this was conjectured by Burns and Katok in the 80s, and this is around the time that those counterexamples for the length spectrum not determining the metric were known. So this was originally stated for two metrics on the same manifold M, and so then you can make sense of what it means for these length functions to agree. But because it was a function on the fundamental group, it actually makes sense so long as you have a way of identifying the fundamental groups. So the content of that remark is that we can ask the question more generally without necessarily assuming M and N are a priori diffeomorphic. And the conclusion, though, is that they will be diffeomorphic. So it just makes sense to ask the question slightly more generally. And so whenever I write two pairs M and N throughout the talk, I'm always going to be assuming that they have the same fundamental group so that I can compare the length functions. Okay, so this is a conjecture, so it's still open. But before I tell you about what's known, I just want to say a bit about the intuition behind it. So I already said how it's related to this inverse spectral problem, but I also want to say how it's related to dynamical systems, because a lot of the intuition and the techniques, at least for solving this in cases where it's known, comes from that. So there's an underlying dynamical system here, which is the geodesic flow. So this is a flow I'll denote by phi t. It's a flow on the unit tangent bundle of M. So we start with our unit tangent vector. There's a unique geodesic with those initial conditions, unit speed. So we follow it for time t, and then that tangent vector is going to be the image of our flow. And you can always do that for any Riemannian manifold, but the point is that in negative curvature, so we're assuming the sectional curvature is strictly less than 0, this flow is what's called Anosov. Another word for that is uniformly hyperbolic. So I'm not going to say the precise definition of that, but basically the point is that there's a whole rich theory of Anosov flows where periodic orbits play an important role. So maybe I should just write that periodic orbits this flow phi t, these correspond precisely to closed geodesics, whose lengths we're interested in measuring with respect to the Mark length spectrum. And just whatever an Anosov flow is, there's a lot of strong results about periodic orbits of this flow. So there's some things you can do about approximating certain trajectories by periodic ones. So one of these facts is called the Anosov closing lemma. So that's the picture up there. So I'm going to explain it because it provides some intuition for the conjecture, but it's also going to come up at the end of the talk again. So I want you to remember the picture. So maybe I'll draw this on the board as well. So what this says is if you have some V, so V is a point because the flow is happening in the unit tangent bundle, and you have some trajectory that's not quite periodic, but it comes back almost close to itself, then what the Anosov closing lemma says is that there exists some W. W is somewhere near V, and it's going to closely shadow it, but this orbit is actually periodic. Okay, so this is a very strong statement. It's not completely obvious because whatever an Anosov flow is, it's a chaotic flow. It's very sensitive to dependence on initial conditions. So like if you just take your V and move it a bit, those orbits will exponentially diverge. So it's not clear that if you just pick some nearby W, it's going to happen. It's a very well-chosen point, but it's this very strong result. So there's this general principle in hyperbolic dynamics that even though it's hard to study individual orbits because they're kind of unstable, you can still say a lot about the overall orbit structure of the flow. So what do I mean by that? This Anosov closing limit tells you that you have lots and lots of periodic orbits. So the picture, maybe the way I drew it, this blue orbit looks kind of weird, but it's actually very, very common by a sort of general foundational result in dynamics called Poincaré recurrence. Whenever you have a flow that preserves a certain finite volume, you know that almost every V, if you wait long enough, it's going to come back close to itself eventually. So there's a lot of orbits like this. They're just very, very long. And then this Anosov closing lemma tells you you have lots and lots of closed geodesics. So this tells you in particular closed geodesics are dense and they see the whole space. So that's good. But it's much stronger than that. Anyways, all of this is to say is that if you know what an Anosov flow is, it's very natural to expect the periodic orbits should tell you a lot of information about the flow. And then there's this sort of standard dynamical fact, which translated into our context of geodesic flows gives you the following thing. So let me just let phi t and ct denote my two geodesic flows coming from M and N. So M and N always, they have the same fundamental group. And let's say that the two underlying metrics have the same Mark length spectrum. Then dynamics tells you that these flows are what's called conjugate. So a conjugacy of flows means that you have some homeomorphism between the spaces you're flowing on. So in this case, I have a map between unit tangent bundles, and it commutes with the flow in a time-preserving way. So basically what you should think of this as saying is that the dynamical systems are isomorphic. So this intuition from dynamics basically tells you that you know everything about the underlying dynamics. So that's very useful for the proof, but it's still very far from the answer because this is just a map between unit tangent bundles. What we actually want to say is that if the length functions agree, the manifolds are isometric. So we actually need a map F that goes from M to N. And this just gives us a map of unit tangent bundles, and it's not clear at all that it's going to be fiber preserving. It's also not clear that this map you get is differentiable, et cetera. So it's still a fundamentally geometric problem, and it's still an open question. But let me just talk about what's known. Okay, so before I tell you the state of the art, I just want to talk about a simple example. So we're going to consider a special case, the special case of hyperbolic surfaces. So we're going to assume the dimension is 2 and the curvature is constant, say equal to -1. And here Mach length spectrum rigidity is true, but actually something more is true. So you only need to check that these length functions agree on a certain finite set of free homotopy classes. So the fact that you only need finitely many is perhaps not too surprising if you know that Teichmuller space is finite dimensional. So the space of all possible metrics of constant curvature -1 up to some appropriate equivalence that you can put on this given topological surface is going to have finite dimension. It happens to equal that number in terms of the genus. So I'm just going to briefly explain why that's true, but that's just to serve as motivation for the talk. I'm not really going to use this later, but basically what you do is you take what's called a pair of pants decomposition of your surface. So you can cut up the surface along certain closed geodesics so that each component looks like a pair of pants, which is this thing on the right. And then because we're in constant curvature -1, or if you like, this is a Riemann surface, it has a complex structure, holomorphic functions are they're very rigid. We know that the hyperbolic metric on the pants is going to be completely determined by those 3 lengths, L1, L2, and L3. And so the lengths of all of these curves in my picture, that's going to be half of the dimension of Teichmuller space. And then the standard thing is you also need to say how to glue the pants back together to get back your surface, because if you twist as you glue, that's going to change the isometry type. So anyways, the fact that you need these 3G minus 3 lengths and 3G minus 3 twists is sort of the standard way to see this as finite dimensional. And then something that's less standard but also true is that you can get those twists from lengths of additional closed geodesics. So basically the finite set that I'm referring to includes those curves, and then you need some that are transverse to kind of tell you how it's being glued. Okay, so that's nice, but none of this works in variable curvature whatsoever. So the problem is, of course, if I don't require the metric to have constant curvature, then I can just perturb it, and I can perturb it on the interior of one of these pairs of pants, and then I've changed the metric, but not the lengths. So there's no way you're going to have this finite set of parameters that tells you the metric up to isometry. So the techniques are completely different in variable negative curvature. So in variable curvature, this is what's known, and the methods are all going to be using dynamics of the geodesic flow in one way or another. So for surfaces, this was done by Otal and Croak independently in the 90s, and they're basically directly showing that that map of unit tangent bundles you get from the dynamics that I was talking about earlier, they're showing it's fiber preserving. But their method really doesn't work in higher dimensions, because what they're using is, if in dimension 2, if you have 2 geodesics that look like this, then you know they intersect, but in higher dimensions, you don't know that, so it doesn't really generalize. Okay, nevertheless, in higher dimensions, it's known if one of the 2 metrics is locally symmetric. So that was done by Hamenstadt using work of Besson, Courtois, Gallo. So this is actually going to be the setting for the main result of the talk. So later on, I'll break down for you what each of those 2 individual papers are doing. But for now, I want to finish talking about the history. So for a while, this is all that was known about Mach length spectrum rigidity. But then much more recently, in 2018, there was a breakthrough solving this conjecture locally by Guillermou and Lefebvre. So locally just means the metrics are close. And then they have this implication that the lengths determine the metric. So basically, the statement is that there's some K that depends on the dimension, and there's some small epsilon that depends on your starting metric, G0. And then if you take any other metric G that's sufficiently close to G0 in the CK topology, and they have the same Mach length spectrum, they show that they're isometric. So basically G0 can be whatever you want. Doesn't have to be locally symmetric or anything like that, but then the G needs to be nearby. Okay, so as I said on the previous slide, since we're in variable curvature, there's just no way you would ever be able to upgrade these results to rigidity on a finite set. Just if you only have finitely many geodesics and you're in variable curvature, you can just perturb the metric, as I was saying earlier, and so you're never going to be able to strengthen this conclusion in that way. But it's still natural to ask, okay, what if I can only measure the first billion geodesics? Can I still say that the metrics are somehow close? That's the best you could hope to do in this infinite dimensional setting. So that's going to be the key question for this talk. So what if I only know that I can measure these geodesics up to some certain length? Then I want to say, are the metrics close? So yeah, I'm assuming they only agree on some finite set. So I'm thinking of that finite set as the set of all conjugacy classes whose lengths are at most some number, capital L. So you want to think of that capital L there as being a really, really big number. It's like the length of your longest possible measuring tape that you have available. And then I want to somehow estimate how close G and G0 are in terms of L and get that as L goes to infinity, I recover that they're isometric. Okay, so intuitively, it seems like this should be true, but all the proofs of the results I mentioned on the previous slide, they're all using dynamics, which basically means they're looking at limiting procedures where you look at longer and longer closed geodesics. So later on, I'll maybe give a more concrete example of what I mean by that. But for now, I'm just saying that they're using infinitely many geodesics in a very crucial way. And so the way I approach this problem is in two separate parts. So first, I use this information about finitely many lengths to get approximate control of the full Mark length spectrum. So that's that downward arrow there. I'm basically saying if I know how to measure the short geodesics, then I can still say the long ones are roughly equal. And now that I have information about these really long closed geodesics, it's more tractable to kind of say something about the metrics and kind of upgrade existing rigidity results to this approximate setting. Okay, so I'm considering this question overall in cases where we already know rigidity holds. But let me just tell you now the statement of the first part. So this first part, I'm actually able to get a general statement just for negatively curved manifolds in general. I don't need to restrict to cases where we already know rigidity. So here's this statement for the first part. So I just have M and N are compact negatively curved manifolds, same fundamental group. And then I'm going to assume that the sectional curvatures are between these two constants. So I always have such constants because they're compact manifolds. I'm just giving them a name. So there's these bounds lambda and little lambda. And then the statement is if I know these length functions agree on this finite set of geodesics up to length L, if L is sufficiently large, then I'm able to say that for all closed geodesics, the lengths are roughly the same in the two metrics. And by roughly the same, I just mean that the ratio is close to 1. So you can see it's between 1 plus minus something. And this something improves as L goes to infinity because the exponent of the L is negative. Okay. And the whole point is that the constants involved only depend on certain concrete geometric and topological information about the metrics. So the premise is basically I have some metric that I don't know anything about, and I'm probing it by measuring finitely many of its lengths and comparing it to a metric I already know. So I really don't want my estimates to depend on mysterious things about the metric G0, because the whole point is I don't know what it is. And so a lot of the hard work and the result is just figuring out what the dependence of all the constants is. So it depends on the dimension and the fundamental group gamma. So that's the topology, which is fixed to begin with, to even be able to compare the lengths. And then in terms of geometric information, I just need to know these sectional curvature bounds and then the injectivity radius of one of my metrics. So in negative curvature, you get that from the length of the shortest closed geodesic. So basically I need to measure like 1 billion geodesics and then maybe one additional one. Oh, and then another thing is there's actually a slightly stronger thing I can say. So the premise here is that we can only measure these finitely many geodesics. We might as well also assume we can only measure them up to some error. So it's more natural to assume that instead of this finite data being equal on the nose, that you actually only know that up to some error. So let's just assume that that's between 1 plus minus delta now instead of there ratio is always equal to 1. In that case, I just pick up a plus minus delta in the final estimate. It's just easier to explain in the case where delta is 0. Okay, so that was the statement of this first part here. At the end, I'll say a little bit about the proof of that, but right now I want to talk about the second part of the story, which is sort of upgrading marked length spectrum rigidity, doing like an approximate version of it where we only know the length functions roughly agree. So I'm going to take that to mean the conclusion of the previous theorem. So I'm going to take this squiggly equals of the length functions to mean that their ratio is close to 1. And then I want to say something about the metrics. So the setting in which I'm able to say something about this is when we're in dimension at least 3, and one of the two metrics is locally symmetric. So this is one of the cases I mentioned early on about when marked length spectrum rigidity is known. Okay, so now I have such an n, and then I have some other m, which is homotopy equivalent, has length functions that are close to that of n. And then the conclusion is that the manifolds are almost isometric, so meaning I have some map f from m to n, and its derivative is close to 1. And close to 1 depends explicitly on epsilon in this way. So n here is the dimension. And again, the point is that the constant depends only on the topology. And in this case, the bound on the absolute sectional curvatures of my mysterious manifold M. Yeah, so I guess another way you could write this is if you wanted, you could just say like, these two metrics are C0 close. But I mean, the way I think about it is there's this map and the Lipschitz constant is close to 1. So it's like almost distance preserving. It's almost an isometry. And then also I can get this, the assumption of this theorem from only finitely many lengths. So I can get some kind of conclusion like this from only measuring some large finite number of closed geodesics. Okay, so for the rest of the time, I want to give some idea about the proofs. So I'm going to start by telling you how this is proved in the case where epsilon equals 0. So that's when we assume that these length functions are the same and we want to show that m and n are isometric. So as I said at the beginning of the talk, this was proved by Hammenstadt, also using an entropy rigidity theorem of Besson-Courtois-Gallot. So now I'll just tell you what each of them actually did. So what Hammenstadt shows is that the marked length spectrum determines the Riemannian volume. So if you have these two length functions are the same, then the total Riemannian volumes of m and n are the same. And for this, she doesn't actually need n to be locally symmetric. This is a more general result of independent interest. So she just requires this technical condition, which is that the geodesic flow of n has C1 Anosov splitting. So that's some dynamical thing. In general, geometrically, it basically means how horospheres depend on the base point and the boundary at infinity. I guess another thing I could say is that this is satisfied for quarter pinched negative sectional curvature. But anyways, whatever this is, the point is it's C infinity for locally symmetric spaces. So that's what we're going to focus on for now. So if n is locally symmetric, then Hammenstadt gets marked length spectrum rigidity out of this using a theorem of Besson-Courtois-Gallot. So for this theorem, it's super important that n is locally symmetric and that the dimension is at least 3. And then if you have some other m that's homotopy equivalent to it, they tell you how to check if m is isometric to n. So you have to check two things. So the first thing is you need to check the volumes are the same. So Hammenstadt does a lot of work to ensure this. And then the other thing you need to know is that the topological entropies of the geodesic flows agree. So there's a lot of ways to think of this number. It's also the volume growth entropy of balls in the universal cover. But anyways, for us, maybe the easiest definition to use is the following thing. So it's basically the exponential growth rate of periodic orbits. So we're just looking at how the set of all conjugacy classes whose lengths are at most t, how the size of that set grows exponentially. That's what this number is. And anyways, from this definition, it's clear that if your two length functions are the same, then the two entropies are going to be the same. You just get that for free because you just see an L in the definition. So that's basically how a very rough outline of how Mark length spectrum rigidity works in this case. And then my proof of the approximate version of this is going to consist of the same two pieces. So I'm going to show that if I only know the length functions are roughly equal, then I'm going to show the volumes are roughly equal. So this is the statement I get for the volumes. So again, I need this technical condition. I don't need locally symmetric. This holds for quarter pinch sectional curvature. Okay, so if I have an n and then my m has lengths, the ratio of the lengths is close to 1, then I get that the ratio of the volumes is close to 1. So let's just unpack what this estimate says. Okay, so first of all, if I just take g and rescale it by 1 plus epsilon, or maybe square root of 1 plus epsilon, so that that assumption holds, then the volume is going to rescale by 1 plus epsilon to the n, where n is the dimension. So those 1 plus minus epsilon to the n terms have to be there. And then I have these other weird terms that depend on the universal cover of n. And like that alpha, epsilon to the alpha is the Holder regularity of something that I don't want to talk about. But again, I'm really interested in this when n is locally symmetric. So in that case, I can do some work to improve what this estimate is. So for free, I get that the constant depends only on the dimension, just because there's only 3 to 4 given negatively curved symmetric spaces of any given dimension. But then I do some work to show that this epsilon to the alpha can be improved to epsilon squared. And yeah, so in that case, that term is much smaller than the one that has to be there because epsilon is really small. Okay, so that's the statement about the volumes being roughly the same. I'm going to skip over the proof of this. Oh, maybe I'll just say one word about it. So basically, the starting point is that the volume of M is determined by the total Liouville measure of the unit tangent bundle. So that's the measure you get by putting Riemannian volume on the base M and Lebesgue measure in the fiber. So from what I said, it's clear if you know the volume of M, you know the total volume of the unit tangent space. But then we just forget about that and use that it's an invariant measure for the geodesic flow. And that basically means that the measure is going to have a different local product structure. So you can look at like locally d mu is going to be d lambda times dt. And so this dt is just going to be one-dimensional Lebesgue measure in the flow direction. And then you get some transverse measure on what's called the space of geodesics. So the space of geodesics is just, I wrote over there, you take the unit tangent bundle and quotient by the geodesic flow. So we identify the two vectors there, v and phi tv. We identify, those are on the same flow line, they're identified. And so those blue orbits or spaces are points in this space. And anyways, the upshot is just that to show the volumes are the same or almost the same, you kind of do two separate arguments to consider how the lengths affect the two measures separately. And for the dt part, I'm not going to say anything about this, but I'll just say that for the dt part, that's that dynamical conjugacy I mentioned at the beginning. You had that map that takes geodesics to geodesics in a time-preserving way, and that's going to basically tell you the dt's agree. And then you have to figure out what happens if the lengths are almost the same. But anyways, I don't really want to spend too much time on this. I just want to, okay, yeah, so I can show that the volumes are roughly the same then. Okay, and then to get the almost isometry, it's sort of an exercise again from this definition to see if the ratio of the lengths is close to 1, the ratio of the entropies will be close to 1 as well. And so my theorem about having the almost isometry is really like an approximate version of this BCG thing. So if the volumes are roughly the same and the entropies are roughly the same, I could compute the derivative of that map and estimate that it's close to 1. And I'm not really going to say much about that. I do want to say how I'm able to get say anything about any of this stuff from only finitely many geodesics. So like earlier in the talk, I said that the proofs are all using like limiting procedures, looking at longer and longer closed geodesics. So one of the easiest examples of that is this entropy here. So we're taking something where we're looking at a limit of longer and longer geodesics, and it's clear that if you mess up, say, finitely many lengths, you're not going to change this h of g. But on the other hand, if you only know finitely many, what can you say about it? So I just want to briefly sketch how that argument works. So as I said, I don't really do this directly looking at the entropy. I just go say that if we know that the length functions agree on that finite set up to length L, then I just show that the ratio of the lengths is roughly the same. So let me just explain how I do that. And we're going to use this Anosov closing lemma here. That's why I drew that. So the starting point is I'm going to take the unit tangent bundle of M and cover it with flow boxes. So what are flow boxes? I take some local coordinates in the unit tangent bundle where this is the flow direction. Then we take some local transversal to the flow, and then we thicken it by delta in the time direction. So that's some open set in the unit tangent bundle. It's compact, so you can cover it with finitely many of them. You need M of those. That somehow depends on delta. We're going to gloss over what exactly that dependence is. And then here's the trick. So with respect to this covering that I've fixed, I'm going to make this definition. So I'm going to say that a closed geodesic is short if it visits each flow box at most once, and otherwise it's long. So what do I mean by this? This is your transversal. Then you have V, which is tangent to a closed geodesic. If you apply the geodesic flow, it goes up out of the box, and then it spends some time in the unit tangent bundle and comes back because it's a closed geodesic. And I'm just saying that it's short if it only went through each box at most once. That's what that statement means. And then I'm using the words short and long because a short geodesic is going to have bounded length. So it's going to have length at most L, which is delta times the number of boxes, because I've just defined it to be stuff that only spends time at most delta in each of my finitely many boxes. So I'm going to think of this L as the L in the statement of the theorem. So I'm going to assume that I know the Mark length spectrum is the same on this particular set of geodesics. And then I would like to say, what can I say about the really long ones? So I'm going to take a long geodesic gamma, and I would like to compare what its length is with respect to G and with respect to G0. Sorry, rather the length of that free homotopy class. But because this geodesic is long, that means it returned to one of these boxes more than once by definition. And yeah, so this is a picture in the unit tangent bundle. And so basically that means that before it closes up, it comes back close to itself because I've chosen the box to be really small. And so this time when it comes back to the box but doesn't actually close up, this is one of these almost periodic orbits to which you can apply the Anosov closing lemma. So the Anosov closing lemma says that, okay, nearby I actually have this closed geodesic that's near it, and yeah, it's a closed geodesic. And then I can do the same thing to the second half of this orbit. And so now I have these two shorter closed geodesics, and I know that the length of this big one is roughly the sum of the small ones. So there's some error term here that depends on delta. Okay, so for simplicity, let's just assume these gamma 1 and gamma 2 are already short, and those are the ones I know how to measure. If not, we can just keep iterating this argument. Yeah, so basically, I know how to write gamma as the sum of things that I understand, and so I want to just push that over to the other manifold n. So you have to be careful. You don't want to do this argument separately in n, because it's just not, you would have to fix a different covering, and it wouldn't be clear that you would get the same free homotopy classes in your decomposition. Okay, so there's this detail that I guess I'm not really going to explain much, but there's something called an orbit equivalence. So we have a map from the unit tangent bundle of M to the unit tangent bundle of N that's going to send geodesics to geodesics, like flow lines to flow lines, not necessarily in a time preserving way, because we don't know that the lengths of the periodic orbits agree, but basically there's just some way that I can push this picture to the other side. So I have some picture like this on the other side that took closed geodesics to closed geodesics, and it's the same free homotopy classes. And if this map is continuous, then I still know if those three curves were near each other on the left, they're going to be near each other on the right. So I still have that this gamma is roughly the sum of these shorter ones. Okay, but to figure out what error term to actually put there, I need to know something about the modulus of continuity of this map that I used. So let's say it's like beta holder continuous, then I can put something of this form here. And so basically the idea is, now that I have these two formulas and I know that the lengths of the gamma 1s are the same, the lengths of the gamma 2s are the same, I can just do a calculation to estimate the ratio of the length of gamma in the two different metrics. So that's the rough sketch of the proof, but as I alluded to at the beginning, the hard part here is figuring out what all the constants are, because I'm using all these results from dynamics where they're working with a flow on like a fixed manifold. So for example, this constant C here in my error term, they'll care about showing it doesn't depend on delta, but not how it depends on the ambient manifold. So a lot of the work is sort of translating this dynamical stuff into my particular geometric context and kind of figuring out how it depends on sectional curvature, ejectivity radius, et cetera. So yeah, that's the rough idea. And the work is showing what all the constants are so that I can get a statement in the end like this, where I know that they only depend on certain things. I'll stop here. Thank you.